We previously defined the delta function by using a rectangular pulse. However, a rectangular pulse has jump discontinuities, so there are points where it is not differentiable. This time, I would like to define the delta function by using a function that is differentiable arbitrarily many times. Consider the function f epsilon of x, which is equal to 1 over pi, multiplied by sine of x over epsilon divided by x. If we introduce nu equals 1 over epsilon, then the same function can be written as 1 over pi, multiplied by sine of nu x divided by x. As nu tends to infinity, the oscillation becomes faster while the area remains finite. First, we compute the integral of the function f nu of x. Using Euler's formula, sine of nu x can be written as exponential of j nu x minus exponential of minus j nu x, all divided by 2j. So the integral can be separated into two terms. The original integrand, sine of nu x over x, is not singular at x equals 0. It remains finite there, but once we split the expression into two exponential terms, each term separately has a singularity at x equals 0. So we extend the integral into the complex plane and avoid the singular point. Here we continue to use the variable x, but treat x as a complex variable. Its real part is xr, and its imaginary part is xi. The path of integration is originally the real axis from minus infinity to infinity, but the point x equals 0 is singular, so we deform the path around that point by a very small semicircle. In this figure, we avoid the origin on the lower side. Choosing the upper side would lead to the same final answer. Now we would like to use the residue theorem, so we close the contour in the direction where the integrand decays to 0. For the first term, exponential of j nu x, write x as xr plus jxi. Then exponential of j nu x becomes exponential of j nu xr, multiplied by exponential of minus nu xi. The first factor is only oscillatory. The second factor goes to 0 when xi becomes sufficiently large and positive. Therefore, for the first term, we close the contour in the upper half plane, because the integrand decays exponentially. For the second term, exponential of minus j nu x, we get exponential of minus j nu xr, multiplied by exponential of plus nu xi. So this term decays when xi is negative. Therefore, for the second term, we close the contour in the lower half plane. With these contour choices, the first contour encloses the singularity at the origin, while the second one does not. Therefore, the second contour integral is 0 by Cauchy's integral theorem. Only the first term contributes. We evaluate it by the residue theorem. At x equals 0, we multiply by x and then take the limit as x goes to 0. Since the contour is counterclockwise, we obtain a factor of 2 pi j. After cancellation, the result is simply 1, so we obtain this integral is equal to 1 for any positive nu. This is one of the properties of the delta function. Now let us consider the integral from a to b of this function. Introduce a new variable, zig equals nu x. Then the integral becomes the integral from nu a to nu b of this function with respect to zig. If a is negative and b is positive, that is, the interval contains 0, as nu goes to infinity, the integration range approaches minus infinity to plus infinity. Therefore, by the previous result, the limit becomes 1. On the other hand, if a and b have the same sign, that is, the interval does not contain 0, in that case, the limit is given by those integration and the value is 0. So this function behaves exactly like the Dirac delta function. Therefore, delta of x can be defined as the limit of this differentiable function. Application to sources. This is an example of how the delta function is used. In electromagnetics, a source that generates electric or magnetic fields is called a source. The delta function is used to mathematically represent such sources as density. For example, consider a total charge Q that is uniformly distributed inside a sphere of radius a. Then the charge density is equal to Q divided by the volume of the sphere, which is 4 pi a cubed over 3 inside the sphere and 0 outside. So the charge density is an ordinary function of position. But now, what should the charge density be for a point charge? A point charge is concentrated at a single point, so we need a function that represents a finite total charge concentrated in zero volume. That is exactly what the delta function does. If a point charge Q is located at the origin, its charge density is written as Q times delta of x times delta of y times delta of z. Now integrate this charge density over any volume that contains the origin. Because the integration region contains x equals 0, y equals 0, and z equals 0, we obtain 1 from each delta function. Therefore, the volume integral of rho becomes q. That means the total charge inside the region is exactly q, as it should be. In the same way, if the point charge q is located at x0, y0, z0, then the charge density is written as q times delta of x minus x0 times delta of y minus y0 times delta of z minus z0. Instead of writing this in scalar form, we often introduce the position vector r0, which points to the location of the charge. Then we can write the same expression more compactly as rho of r equals q delta of r minus r0. In this way, a point charge can be expressed as a function of position using the delta function. This is why delta functions are very important when solving Maxwell's equations. They allow us to represent very thin, very small, or highly concentrated sources in a mathematically precise way.